Hmm. All right. And looks like we're going. And we are moving this morning. This morning. If it's this morning for you, then you're probably watching this from like Japan or something like that, because it is balmy 2 o'clock in the afternoon in Atlanta. Welcome to the stream. I'm Jason Watts, your, I don't know, like neighborhood friendly automation guy. Is that what I am? But whatever I am, my name is Jason. Welcome to the stream. And if you are coming in on the stream from the greater internet or whatever afterwards, after the stream, and you're looking for some information about what BICO is, welcome. And you could kind of skip ahead. We kind of get moving and started here in a minute. We'll have some chapters here. You can go ahead and skip ahead to the chapters where we start talking about BICO. What is up, everybody coming in? Christoph, welcome to the stream. It is great to see everybody. Mika, it is wonderful to see. And I love the guys that were on Hans's stream with PLC Skills, I can't even say it, PLC Skill Tree. It's a great channel, much bigger than mine, so I'm kind of like grabbing on his coattails, but he did his first stream a couple days ago. Well, I guess it's about a week ago now, and yeah, had a bunch of awesome information in there. I saw Mika in there, so it was great to see everybody. Yeah, so hopefully on this Friday, if you are abroad, that you're, I don't know, either in the middle of hanging out, getting ready to go to bed, or just kind of chilling, relaxing. Thanks for coming, and yeah, we are going to learn today about BICO, which, if you didn't know, this is kind of a Siemens focused channel, and Siemens drives are pretty flexible, and they kind of can do a lot of different stuff. And if you don't know anything about me, my name is Jason Watts. I'm the CEO, founder of a little company called Alpha Industrial Technologies out of the Tuscaloosa, Alabama area. And we primarily are focused on Siemens, and that is because I have about 24 years of experience working with Siemens drives in some sort of capacity. Started diagnosing and troubleshooting them at the bright young age of 14 years old, thanks to my dad kind of having an integration outfit on the side for basically all my life. But yeah, so here on this stream, as you're coming in, just say hey. Like, want to thank the members as you're coming in, and kind of Mika here. He has been a long time member, and I will say I just posted before I got on this stream a little fun video for the members. YouTube wants us to make members only content, and I don't want to keep too much back from the general public, because this whole channel is about kind of helping you on your automation journey. But I do want to add value for the members. Got a fun video that I posted up earlier today, just about my hometown and the little football team we have. But yeah, if you're a member, check that out. And I'm going to be doing just some other things that at first will be members only content, and this will be available for both tiers. But kind of I did a little poll, and I got a couple of votes from the members to kind of the business development side of it. If you are a kind of looking at doing this full time on your own, yeah, there's a little bit of challenges in there, and I'll kind of talk generally about it, generally about the kind of the stuff like in my streams. But I plan on doing a little bit of a series that's recorded. I'll probably be recording that when we get off the live stream. So members, be looking out for that. If you haven't subscribed and you're here, like, check out the channel. There's a lot here for you. But if you're here, hit that like so we can get this out there. We're going to be talking for a little while today about kind of Siemens drives, and I've got my tea with the throat coat. This is the so that I don't know how long we'll be going today, but until I get tired of talking about Siemens drives. So I guess, reserve a hotel or wherever you are, because it could be a while. Yeah, it's interesting. Mika's in chat is saying that he saw the video from earlier. If you are not from the U.S., I don't think you have any comprehension of how serious university football is here in the U.S. So it's kind of crazy. But yeah, today we are talking about BICO, and I've got a couple of different things. And this question actually came up. I can't remember who the user was off the top of my head. I probably should have looked it up, but they were asking on one of my streams about what is BICO, and I guess from the early age that I started into Siemens automation, it's one of those things to where I guess I took for granted the fact that like I just understood what BICO was, and I've talked about it on a couple of other streams. But what BICO stands for, the actual word stands for. I say this, it's binector and connector. I did actually plan for this. I looked up some stuff because you just can't tell because it's Friday. But let me bring up this little document here, and I'm going to show y'all. Yeah, so Lucid, you joke. I'm just trying to look urban, you know, and cool and relevant to the young kids that are watching this. Lucid said it looks cold in there, and it's so I'm joining you from the Alpha Laboratory in West Midtown Atlanta, and it is a little bit cold in here, but it's because we're in a big warehouse space and the air conditioning unit's on the other side of the wall, and so I just kind of get whatever heat gets over here. And I don't know how to wear long sleeves. They kind of bother me, and so I wear jackets. And then yeah, it is what it is. Well, let's talk about BICO. BICO. I gotta go here. Yep. And where does my head fit best? I think it's up in this top corner, out of the way, right? So looking down here, BICO is binectors and connectors. And what BICO, just at a very quick explanation, is, it is the way that you can actually program reprogram and reconfigure the drive internally. And when I first started working with Siemens, it was just with master drives. And so I didn't have any other experience with any other drive technology or manufacturer out there. And honestly, I don't really have that much elsewhere. About the only other stuff that I've ever really worked with and did much of training on drive-wise is the Eaton DG1 series. And I was kind of surprised that, like, yeah, that's a simple drive, the DG1. It's a simple drive. You can go in, you can configure a little bit, but you have a couple of different options to configure it, and then it just kind of does what it does. And then you can set parameters like the gain functions and like all of this different stuff. Well, the reason why that is very different from Siemens is that, yes, there are standard configurations that when you pull up Portal, and we're going to be working with Portal today, and when you pull up Portal, that, all right, it just kind of works for generally most stuff. It asks you a couple of questions. What type of application is this? What type of motor? Like all of that stuff. And then you kind of get going, and you might have to tweak something, change something. Well, if you think that that is similar to that Eaton DG1 where you have a couple of different options, yeah, you're kind of right. But then in a way, you're also missing out on a very powerful feature of these drives. We're going to be working today with a CU240E-2, so a Profi a G120 general drive. I do a lot of work with the S120 because it's like the S120 master race of drives. But I wanted to show you that BICO technology is on every series of drives in Siemens, and what it does is it makes it to where you can actually reconfigure the way the drive works. So there's a link in the description below to this document that I have pulled up right now. It is it's an older document. It's from firmware version 3.2, so very old. I think it's like 2011 or something like that. But I found it, and it goes through kind of an explanation of what the basic principles of BICO is for someone that has no idea what it is. BICO just allows you to, it takes and parameterizes all of the interconnections inside the drives, and then you can take a block and then retake the output from that block that normally is tied into this block, and then you can say, wait a second, I don't want that block. I want the signal from this other place coming in here and plugging in. And I didn't realize that was not a common thing when I first started because I didn't know any better. Like, that was just what I did. On the master drives, they had on the MC master drives and motion control master drives, they had a function block or technology blocks that were called the F01 function blocks. And they had things like electronic gearing and camming and all of this stuff built into the drive for free. Like, you bought the MC drive that was just kind of the higher performance drive, and it had all of this like technology built on to the drive. And honestly, when the S120 came out, there was a lot of heated discussion, I should say, from the current Siemens user base that these F01 blocks weren't duplicated from the beginning. And yeah, I'll show you why it's powerful, because it was all based off BICO. So you have two types of interconnections in a drive, or in really anything. You have bits and words, and then you can have double words and things, but you have an on or an off, a Boolean value, and then pretty much everything else. Everything else depends on how many words you have, but it's a bit or a word or multiple words. And that's what the drive has. So the binector is bit interconnection, and the connector, the CO part, is the actual word portion of it. I'm sure it has some sort of German-backed technology or some word that's behind it that it goes. But so you have inputs and outputs, bits and connectors. So bits and bytes, bits and words, and so you can interconnect. So like, I'm not just going to read this stuff because it's like, you can look up the document, but I'm reading this. Siemens disclaims all liability, blah, blah, blah. It shall be used for its own internal purposes. Huh, interesting. I don't know why they put this on the support website. You can get this document off the support website, so I don't know why they call it, they say that it's restricted. But, so you have bits. Bit inputs look like this. Look like this here. Bit outputs look like this. And you kind of like look at the description, the function. The data flows in to, you plug it in to the curve, and then if you have your curve on your connector, it can plug into like that. So it's like your bit inputs have a way that you can plug it in, and your bit outputs have the curved part of it. So that's the basic portion of what the bits are. Then you have the connectors. They have an arrow or a like triangular side of it, which that just means it's a word or group of words. So it's a real value, integer, percent, something like that. Now we'll talk about this here when we actually dig into using this, that most of the values are in percent base, and we'll talk about that a little bit better later on. Because this, now what can you do with this? What can you do with it? A lot of stuff, actually. Siemens drives, and even the G120, almost went German on us. Even the G120 themselves, which is one of the lower performance drives, it has the ability to essentially be its own control system. You can actually implement a full like PID control system for like a pump. If you're just wanting to regulate a pump, like the pressure on a pump, you can actually do that just built in with the G120. You have a couple of analog inputs, and we're going to do that here in a second. But it's all based around these connectors and binector inputs and outputs. That's what BICO is. So, yeah. Next thing we're going to look at, see if there's anything else in this manual. Yeah. So this document, it's really short because, and this is kind of why when I started first looking at the question of like BICO, and I'm like, well, it's really easy to explain, but it's also like such a big concept that it's difficult to explain. And I realized when I was researching this that there might be a little bit of a lost art or a lost form of communication, shall I say, to people. So if you're fairly new to automation, and I say new, I mean it could be probably 10 years or less, you may never have experienced what I'm about to show you, but because a lot of these features and functions weren't required, especially if you're in the US, like this type of stuff isn't. So I'm gonna pull up the list manual for the CU240E-2, and the list manual is, if you're someone older that's watching this, which you're probably not on YouTube. I'm probably the oldest person that does this content on YouTube, but if you're a little bit older, a little bit more experienced, you may have experienced these function plans and these charts that show you how the drive is programmed. It's kind of a combination of CFC, block diagram, and a little bit of kind of your old control diagrams if you've gone through a control class, maybe at a university or something like that. But this list manual, Siemens used to get a really bad reputation for being extremely complex. And not gonna lie, the reason is because a lot of programmers would use these features that people were not used to using. They were used to programming it in the PLC, leaving it alone, and then just kind of having a speed controller for the drive. Well, a lot of these machines came over, and there's so much functionality built into the drives that it's like, why would I want to use a PLC for this when I can just make it into a drive, have a program, and do this thing really well at the drive level? And so the list manual details out all of the options and functions and how all of those things work. And if you're flipping through this list manual, it shows everything. If you flip through what's called the function diagram section 3, it goes through all of the capabilities and functions. And now remember, I'm in the G120. There's one of these for the S120, and yeah, there's seriously like 20,000 parameters, and there really is. But you still only use like 50 of them in even an S120 system for the most part. But for that one time when you need the flexibility, here you go. And so the list manual is where these function charts are. Function diagrams, though, are a way of kind of showing a program. And what we are going to be looking at is what is called the technology controller. And it's here on page 777. So the technology controller, everyone else would call it the PID controller because that's what it is, but it also it's not just a PID, and we're going to see here it has the ability to have your own control system and all of these variables and all these different things that you have options for, because it's more than just a PID. It is a full technology controller. You can actually create your own torque drive control just with the technology controller on the basic drive or the standard level drive. Get that? This is the standard. This isn't S120. And I'm going to use these charts to show you how BICO works. So this chart here is horrific. And I'm going to move my head out of the way because I want y'all to be able to see this. And you'll also, ooh, I'm killing something. This, and then move this here. Something may not work on my stream after this, but this chart, it just looks horrible. And I don't know, maybe it's just me. Like, I can see the things and it's okay, because when I first started working at a very young age with these master drives, this was just what you dealt with. You pulled open a manual, a physical manual, by the way, like printed out, like with all the dead trees and all of that from it. You opened it up and you looked at these charts, and these actually tell you how the drive interprets it. This is a programming language in essence. And the way, instead of typing in like variables, the BICO are those variables. So you can see, we kind of talked earlier about the shapes of the different objects mean something. So you see all of these pointed points here, you immediately think, okay, that's some sort of BICO. And in this case, it's connectors, it's word values. And let's just kind of take and look and see what is going on here in this horribly complex like chart. Well, we kind of see the names here, like this one. So this loop is, let's just step through it, because you actually have like inertia compensation, so a DVDT filter, so like feed forward. You have your ramp function for your set point. You have filtering and stuff for your actual value. All of this is coming through. And so let's just take a look at our set point path for a second. If we're used to kind of looking at this on the drive level, yeah, I don't think there's a derivative action on this controller. I don't think there's a derivative, but I could be wrong. Let's step through it. So in this one, you're bringing in your set points, and you have a couple of scalar values, which are parameters. Now remember, parameters, and this is something also to think about, parameters you can change manually. Kind of think of it, I have to type it in. So you're either going to be typing that in inside of Portal or Starter, or you can use acyclic communication if you're communicating. But let's just assume that we don't have a PLC in the loop here, and we're wanting to implement this feedback control on this G120 this way. Well, you have this point to where you can bring in a set point and then multiply it by a scalar. And by default, the parentheses, let's zoom in a bit more. By default, you have a 0 setting. And so that is the interconnection. This is not connected. I'm going to show you here in a second how to actually connect these in Portal, but let's continue to just step through. And so you can just trace through, just like a control diagram for like a that you might be used to in your controls class at university, you step through, and we've got a ramp function. And so you have a ramp up time, P2257, and then a ramp down time, P2258. So you can put in a ramp up, ramp down type of filter on it. Then you have an actual filter. So ramp function, a filter, which by default, if you're looking at it, default, this is 1 second ramp up, ramp down. Default 0 seconds of filtering. And then you can go through and look at this block here. It's an inverter block. So there's this parameter 2306. If you want to have an inverted control, so when a negative, so like it inverts the direction. So like if a negative discrepancy needs to cause the opposite, like to slow down, in order to make up an error, then you have to do an inverse controller here. And so you have that error, you can step through, you have a couple of more of your devices. So here's your actual PI controller. So your proportional KP, and then your integral portion. So this is your actual control here. You have a couple of different options. You can have your parameter 2280 for a fixed KP, and then you have your parameter 2285 for your fixed integral portion. Now, we will jump over to this other thing here because some systems, mostly with high inertia, will need what's called adaptation. So as you go faster, you want a less responsive controller. So like as the actual speed gets higher, or the actual value gets higher, you want a different settings on your controller. That's called an adaptive controller. Well, this has adaptation here, and you'll notice here on this, there's this number here. That's not a parameter. That is a function diagram number. So we're going to come back to that. So put a pin right there, and let's just trace through. So we know that if this was a speed controller, like on a drive, we have a speed set point, and then the output of this, of the proportional, or the PI controller, the speed controller, is going to be a torque. And then here, you may or may not be familiar with the concept of inertia compensation in a drive-based system, sometimes called feed-forward control, torque pre-control. But you can have a pre-control signal, which I'll show you that kind of, I guess it's kind of up there. I'll show you in a second. But that comes in here. So you can add in an additional kind of pre-control for it. What you would think is, like, for example, if you have, if you know you need to heat something up, you know that you need at least 5 amps of power going out, just in order to start heating up. Well, you don't want your proportional controller maxing out, or your integral maxing out and then having to correct. So what you would do is just say, okay, if I need to change, I have to have 5 amps. So I would plug that pre-control signal into that path and just say, hey, I've got to move, so just put 5 amps out there. And that's what the pre-control is. And so kind of moving on through, and then it has some filtering. So output scaling, you can take the output and then scale to a different value. So if you're going to different units, say for example, you have 0 to 100% on your pressure sensor equals to a 20% change in your drive speed. Okay, well, you can scale that here. And if you notice there that these values are connectors, whereas they're not parameters, they are connectors. So the difference being, if you don't have an arrow or a place to plug something in, then like this, that is a fixed parameter. Here, this is going to be a connector binector. So this is a technology controller. A lot of stuff in here, but it's just all of the different options that you have in order to tune this PI controller. So the last thing we were kind of talking about, there is an option for you to get a signal back to the kind of a compensation, like a pre-control. That's a post feed forward signal, and then this would be a pre compensation. So you have your derivatives and all of this stuff. Okay, very cool. Cool, Jason. What does this mean? How do we use this? This is annoying, this because it's like so big and all of this crap all over the place. We talked a second about, before we get off of here, this 7959, this number here. If we wanted to do adaptation, then if we wanted to do adaptation here, we would need to figure out what this 7959.8 is. Well, if you go down to the bottom of this page, here is the those page numbers, because that is actually a function diagram number. And so this function diagram is 7958. And so we would want to go down to 7959 and then find section 8 right here. And then we would find our value. So there is KP adaptation, TN adaptation. And so we can now back our way into these different values here. And you're like, Jason, that is a lot of stuff to just talk about. What is BICO? Well, let's be honest. If I just gave you the definition of BICO, this would be a 5-minute stream, and I don't even think anybody would realize that I was on. What's up, Ali Reza? Why are you awake? Isn't it like 2 o'clock or something like that in the morning over there? We're talking about the technology controller and how to do it. So, and so like if you on your Friday night, Ali, if you want to take another Friday night and learn about some drives, I guess that's the thing. I mean, that's what I'm going to be doing later. But sometimes I feel sad. Sometimes I don't. But let's flip over to Portal for a second, because we've got some cool stuff that I want to show you actually how to go through this. And again, if you're not aware, another benefit of being membership at the highest level is that I will upload this, the project that I have here. Whatever we do in these projects on stream that I'm playing around with, that we're creating and making, I put these projects into the member folder and make it available for the members. The highest level members get the full project, and then the first tier gets kind of the user data types and things like that. But again, new to the membership page, you all get access to the extra features, which right now is just a cool video with some football in it. Yeah, you're about to celebrate a new day, Ali. Ali Reza is our resident person that likes to stay up all night and think about automation. So I appreciate him being on. So let's see. So what we have here is I've gone ahead and just thrown in a a drive. I just call it pump drive. So it's a G120 with a CU240E-2, which, if you're not familiar with how to do this, in your drive and starters, select SINAMICS drives, SINAMICS G, G120, control units, find your control unit and drag it into the screen. And then when you click on it, you can click on device view, and then you can select your power module. I have thrown in and just drag that in, drop it onto the screen here. I've already done that for this other one, frankly, because I had to find how to turn all this stuff on. And so I had to make sure, because I'll be honest with you, I went for a very, very long time only using starter. Even when start drive was available in Portal, I was just more comfortable with it. But because I was only doing drive-based projects. And yeah, there's some things that you can do in starter that are a little bit better and a little bit easier to do in starter over start drive. But all that to say, I had to make sure that I knew how to do all this stuff. So once you bring in this pump drive, it'll show up over here on your project tree. If you go to it, what I did was I went ahead and put in some just random values, not really random. So I went to online not online diagnostics. I went to commissioning. Commissioning, and then I went to the commissioning wizard. And one of the things that I always like to do, and again, I like to have all of the options because I know what they mean. And as you're kind of going through, if you're watching these channels, you probably have a little bit more understanding of what actual everything is actually meaning. But yeah, so in order to have all those options, I always select this expert and then just go through. I'll just show you ramp function in the drive. Doesn't really matter on how you have this set up. Field bus with data set changeover. We've talked about that and other stuff, but this is all just kind of the standard stuff. NEMA, because I'm in the US with the 60 hertz line, 480 volts, and then just clicking through on all of this. Motor data, this is a 10 horsepower drive, so 480, 12.5 amps, 10 horsepower, 90% motor efficiency, 1760 RPM. Kind of blowing through all of this because this is just standard stuff. I will say, here's a couple of things that I do want to show you. That by default, if you're in the US, which most of y'all watching probably aren't in the US, set your reference speed to 1800. By default, it's 1500, and that's based off of like a 50 hertz line. 50 hertz four-pole motor is going to get you 1500 RPM. In the US, that's 1800 RPM. And if you don't change that on your PLC side, if you're working with PLCs on it, your reference speed is going to be different. Because remember when I told you a little bit earlier about how the connectors are mostly in, and I just realized that this screen, it doesn't like this screen. Hold on, let me do something. Window capture, properties. Can I do the whole wing? Because I realize that my whole screen is not being captured, so you can't see the commissioning wizard. And I'm like, and I'm showing you this stuff on here that you can't see. Let's see if I can get this on there for you. Window capture method, blah blah blah. Nope, cancel. Let me add this. Add a display capture. Sure. Okay. Yeah. There. Now you can see it. Sorry about that. So this is what I was talking about here. This reference speed is quite important in when you're working with these connectors, the connectors specifically. This is the reference speed, but we're going to talk in a second about just the entire group of reference variables. as you're going through this wizard, this is kind of the last page of it. I just kind of jumped over everything. Basically, the only thing that really matters on this is the expert is selected on the very first screen for me. That gives me the full control over all the different options that show up here. Everything else I just kind of went through. And so under this important parameters, these are important parameters. Here's the thing too. I generally, even on an 1800 RPM motor, generally the mechanical maximum speed is going to be allowed to go over that 1800 RPM, but you just go into a mode to where you don't get any torque out of it, or your torque goes down because you're in what's called constant horsepower or constant power range. Above your rated speed, there's some weird stuff because you can't get more voltage on those windings, and so that's what's going on. So your torque saturation starts to go down. Anyway, BICO. So let's just click next. This doesn't really matter at this point, and we're gonna finish. And once you get finished, we're going to go over to parameters. So, and normally, and you can see I was kind of playing around this before. Normally it shows up like this, functional view. You get that. Before we move on, I want to show you a little bit, kind of, I used to get in trouble for doing this when I was working as an application engineer for a Siemens distributor. The Siemens guys, like the motion control specialists and everybody that worked for Siemens, they would see me teach a class or whatever, and they'd be just kind of sitting over there, and they would get on to me because I would jump straight to the expert list. I would go straight to the parameter list, and they're like, you don't need to do that because it makes stuff look harder than it is. And I'm like, okay, yeah, I guess you're right. I guess you're right. But the problem is that in order to set some of these variables, you end up having to go to the parameter list. And if you've never used a parameter list, then you kind of get lost. So I'm going to show you something real quick. By default on a G120, this little value here, up in this top, this top form, and does that even like show that I'm clicking on that? No, it doesn't. My goodness, that stinks. But so I'm clicking on here, and you have, let me do this. Yeah, so you have on here that a couple of different options: standard parameters, extended parameters, service parameters. Well, by default on the G120, it comes up with the standard parameters here. Well, that doesn't quite get most of the things that we're going to be working with. So what you want to do when you first go to the parameter list on a G120, this S120, you get expert, or you get these extended parameters by default. I don't know why the default is on the S120s different, but lots of parameters. And this is why the Siemens guys would always get on to me, because they're like, we've got these guys that say Siemens drives are complicated because there's so many different parameters. I'm like, yeah, but you only use like 5 of them. And they're like, yeah, but you're showing them 20,000. And I'm like, but I don't really, because I click here and I want to go to parameter 2000 because these are what's called our reference parameters. So I click in the number column and say 2000. And I just type it in on my numpad and it goes straight to it. I don't have to search. I don't have to do anything like that. If you know the parameter, click in the column, type 2000. So we set this before, and it was this reference speed reference frequency, and we set it to 800 or 1800 RPM because I'm here in the US. Well, here's a couple of different things that I wanted to show you about these references, because everything actually in the drive isn't real numbers. I should say most everything that is in the BICO are percents, and they are percent of these values. So percent of parameter 2000 through 2006 are your reference parameters. So if you have a speed that is being shown in your drive, like R63, and you pulled that up, it's not going to say 1,000. Well, I guess it might say 1,000, but that would be, it would be 1,000, but that would be in like a decimal word. And so if 1,000 would not be anywhere as fast as you would think it would be, because 1,000 is a percent of 16,384, a word. So 1,000 would be what? Like 10, not even 10% speed. Yeah, it'd be like 5% speed. You're expecting it to be going over 50% speed, or whatever that would be. You're looking at like 60% speed, and it's not even doing 10, and you're like, what is wrong with this? It has 1,000 set point. Well, no, that's 1,000 is 1,000 scaled 16,384, which is in a 16-bit word. You have a sign, plus or minus, and then you have 1 bit that is available for going over 100% speed. You need to be able to go up to 200% speed, and so that's the 15th bit. So a 14-bit number, if you convert it, it can show up to 16,384, or and so that's why you are scaling to 16,384. Anyway, if this number is off when you're reading that value on a PLC, then you're saying, okay, this is an 1800 RPM motor, so it's 1800. Well, if that was 1500 RPM here, it's scaling to 1500 RPM, and then you think that it is scaling to 18. So that's going to be different. You're going to get speeds that are off. Like you will think that you're getting the right speed, but when you actually go to physically put it on there, it's not going to be reading the right thing. And so like it could cause some mind-bending problems if you don't realize what these reference variables are. And if you notice, there's reference voltage, reference current, and reference torque, power, temperature, all of this stuff. This reference current is I'm about to show my redneck. It's a booger. And because by default, remember, I put a this is a 10 horsepower motor, so about 12.5 amps. This reference current by default is set to the current limit, which is set to 1.5 times the your actual rated amps. So if you're looking, like all of Alpha's systems show the percent, show on our SCADA platform, all the speeds and everything are in percent, and current is in percent. So that way you can immediately know, hey, is my motor running, is it under load? 100% is rated load. It doesn't matter if that's a 10 horsepower motor or a 1,000 horsepower motor. 100% is your rated load. Well, the problem is if you don't set this reference current correctly, then my rated current is 12.5. And so this is 150% more. So the first thing you have to go in, if you're going to be using these things, is make sure that you're looking at the right thing. And what happens on this is if you assume that that's FLA, your full load amps of your motor, you'll be sitting there and it'll be showing 80%, and you're sitting there, and on your SCADA platform, it says, all right, my motor's running at 80%. Why does it keep on tripping out? And then you call me at 2 o'clock in the morning, and you're like, Jason, your system is so dumb. Something's going wrong with it. We're only running at 80% current, and it keeps tripping out on overload. What the crap? And then I'm like, that doesn't sound right. That's not possible. But then I'm like, wait a second, crap. I'm an idiot. I deserve to be woken up at 2 o'clock in the morning because I forgot to change this parameter 2002 to actually 12.5. Let me see something. Sorry, gotta send a text message. And so, yeah, we got to change that. Now, when I'm thinking 100%, when I'm thinking 100%, it's actually 100%. Because in that scenario that I just said, that was 80% of 18.5. And we could do the math, but guess what? That's why we're overloading, because it's sitting there running at over 100% FLA, and so it's heating up. And guess what? The drive will let you run up to the current limit, and it's just going to be doing an I2T calculation, an overload calculation. So anyway, let's go in and talk about this technology controller. So you can either do it the old-fashioned way, like Boomer, me, and look at this nasty chart, and oh yeah, you can't see it. Why can't you see it? That should be the whole screen. There you go. Yeah, so you can either look at this nasty chart and individually look at the different values here and all of this and blah blah blah. And I will say, you're still gonna have to look at that a little bit, or at least it's the easiest way to do it. But if you go over here to in this group, if you go to functional view, and Siemens guys, look, I'm using the functional view. I'm not on the parameter list. I'm better. You go down to application functions, and then technology controller. We're going to talk about these, by the way, as well, but not right now. Technology controller, and then look at the technology fixed set points. Those are the set points that like come in, and these actually correspond to these function plans. So if you scroll up here, you've got a technology function, fixed set points, fixed values, binary selection. So here is that big nasty thing. Here is how it is presented on the portal. So much nicer, I would say. But let's talk about the technology PID controller. And so what's funny is that the Germans, when they did the portal, when they did the G120 in the list manual, they call this thing just the technology controller, and then it's just a bunch of, they call it closed loop control, because technically it's more than a PID controller. And behind my head here is where it says closed loop control, but it's technically more than just a PID controller. And so they're being semantic or pedantic and saying that. And well, somebody was like, hey, everybody else would just call this a PID controller. And so here's what we have. And so the way that you would actually want to connect this, and just comparing the two, let's see if we can, like this value here, by default, we have our technology control set point 1. Default, it's unconnected. Okay. set point source. Let's see which one this is. So this is technology controller set point 1. All right. And by default, it says 0%. What? It's so, yeah. What's up? What's up, measure and cut? How is it going, young sir? But we're talking about some wonderful BICO technology and technology controller and all this stuff. So if you notice in the function plans or in the function charts, it says it's connected to 0. And then over here in TIA Portal, it says it's connected to 0%. Well, that should clue you into the fact that everything is in percent. Because when we go here, this is going to be a percent-based thing. Like, you got to get out of, you got to scale it into the percent. And we're going to show you something here in a second. Because what would be a good set point for this? Maybe, I don't know, an analog potentiometer on a panel, a pump panel. All right, let's go into BICO. Oh, such aptly named. I love it. And let's scroll down to, what is it, like 722? Yeah, 752. So 722 is the bits, inputs and outputs. So we're going to go there, and there is the CU analog inputs value. And you're like, Jason, how in the world would I know how to do that? You just know, right? Like, you just know. Well, guess what? It's actually in the list manual. You can look it up in the list manual like a boomer, and we can go up here and look at inputs and output terminals, connection overview, analog inputs. Right? And analog input 1, status word. Look at that. It's got the bubble. It's got the bubble, which means it's a BICO. And you can plug it in places. So 751. And then that ends up being, look at that. I say that. 750. What? Wait, why is it 752? Oh, it's probably because that's not the right place. Maybe I'm using the wrong thing. Oh, because this is there. I told you I wasn't crazy. So 751 is there, and that's 751. So that is here, analog input. That should be, oh, analog value in percent. So we actually need to be using R755. Man, measure, why didn't you tell me that? Why didn't you tell me I was supposed to be using that? By the way, I'm gonna give measure once, cut twice a hard time, because he is my replacement at Wesco. So let's look at this value in percent. And so again, it's saying, hey, reminder, you need to put a percent in here. And so we're going to do that for input 0. We're not going to scale it. And so now we're going to take in our imaginary little box, and we have our analog pot, our analog potentiometer. That's going to be a 0 to 10 input, right? Well, oh, look at that. We can actually change it to current or voltage based on a dip switch. That's in the list manual. But we connect that connector into our technology controller here. Now, how would we then proceed to connect up the actual value? So down here on this garbage, we closed loop control, we have this like actual value somewhere. Gosh, it's right here. It's rough. So we're looking for parameter 2264. All right, and we could see down here the actual value source would be good. And again, it's in percent. So let's go through. Excuse me. Let's go through and tie this into our analog input, our second analog input, which is aptly AIM analog input 1. Thanks, Siemens. I'm joking, even though that does trip a lot of people up. So the first analog is analog input 0. 0, not 1. Why would you think otherwise? And so that's our analog input. And is that the right one? Yes, it's in percent. So now we have percent, our input, our feedback, and now we can go through and set all of our different things. So we can go in PID control, we can click here. There's our gain factor. There's all of that stuff. Well, what if we wanted our pre-control signal? What if we had something from somewhere else that we were calculating that we wanted to put in there? Maybe, I don't know. What if we wanted the actual value, actual speed smoothed? Why would we want to do that? Because if it needs to move, it needs to move from there, right? And so these are some of the different, like, if it's sitting there generating a pressure on a pump, and the output of this PID controller, you don't have that feed forward of the actual value in there, you're having to change the entire thing. And so essentially your integral component of that controller is always going to be saturated, and it's going to be weird. So if you feed forward like this, and you're going to feed forward, here, then, did I put that in the wrong spot? Yeah, I put that in the wrong spot. No, I didn't. I did not. I did not. So, yeah. So that gives you the actual, like, all right, we want to run at this speed, which is the actual speed, and then you're adding in a change or subtracting off a change. Now that might be the wrong way to do that, because normally I would put in the speed set point of the controller. The speed set point. It's probably not this. It's probably the other. But anyway, you can figure out whatever makes sense. If you're watching this on demand, welcome. You should throw a thumbs up. But yell at me if that's wrong. Yell at me in chat. Yell at me in the comments. I'm wrong every day. Just don't tell my wife. But yeah, here we go. So maybe we would want to do that, and we can adjust all of these things. So we had a question from one in chat, whether this is only 2 control loops, or I guess if it has a D component, and it does actually have a D component, but I'm not exactly sure. It doesn't have a factor that you can adjust on it. So the derivative component is there. Anyway, so let's go through and just say, okay. So that's kind of the general overview of what you could do. Now that's a very specific thing. And then now here's the technology controller as the main speed set point, right? So let's keep clicking through this page and see if we can find where it actually comes in. PID controller active. Yeah, so that's there. So there should be 10 supplementary speed set point. Does that change anything? Let's see. So we're kind of seeing how. Oh, because it goes into the ramp function at that point. So that's here. So it comes in there. which is interesting. After the ramp function, you're kind of adjusting. Okay, so that would be the way that you could set up. That would be a way that you could set up a differential signal that's a little bit better. So you have an overall ramp. The reason you would want to do this, and I just ran into this on a roofing felt line that Alpha was doing, and there's a dancer, which is a way to keep tension in a web, and it's sitting there. Normally it's on the ground, and then there's a roll that goes underneath it. And let me get full screen on this, because there's a roll that goes underneath it. And as the tension increases between these two rolls, that dancer will come up. And so it's used to regulate the tension downstream in the sheet. Well, that uses a PID control on either, in our case, it's an inclinometer, so it's looking at the angle of this, or you can use a pot and have the wiper of the pot be connected onto the arm. But either way, you have a set point of where you want the dancer to be physically in the air. Then in order to raise that dancer up, you have to slow down the entrance. So you have two controlled rolls. They each have drives on them. And you have to slow this one down relative to this one. So you give both of them the same signal and then ramp them up, and you would get a signal that is very similar to what is in what's here. You would get your ramp function signal coming through here, and then you would want this PID controller to just look at the difference. So you want those two motors to be ramping up and down at the same time. But the PID controller, you want it to be creating an offset. So you want this one to be running just a little bit slower than this one in order to raise that dancer up. Then once it gets up to the proper place, it's going to kind of speed up a little bit, slow down, speed up a little bit, slow down, just to kind of keep that dancer in place. So that is how you would do it. I was implementing mine on the PLC and using so I think it's the, what is it? The Cont C or block. I can't remember which one it was, but, and in order to do that, there is this feed forward path on the PID controller, and you feed forward the set point that they're all running at. And then that's what's going. So you already have the set point, and then you're adding in the PID component, and that's exactly what's going on here. So that's interesting. I learned that literally just right now. Thank you, chat. I'm learning with you. This is wonderful. This is absolutely wonderful. Now, what else did I want to talk about before I started rambling on like a mindless person? Oh yeah. So that's kind of generally BICO, you're interconnecting that way. Another way that you can modify the functionality of your system, because, I mean, let's see. What is a PLC? It's got programming, it's got ways to get inputs, it's got ways to make outputs, it has ways to make logic, right? That's a kind of a PLC. And you have some of these like really, I'll say low end, but I guess low feature PLCs, if you call them, I guess logic. Yeah, I guess you'd call them logic or PLCs. But like the Logo, for example, if you've never heard of the Logo logic module, essentially it's kind of like a smart relay almost. Like you could program a little bit of logic into it. It can do decent projects, but it is essentially based on ands and ors and stuff like that. Well, you might think, okay, well, what if I have two push buttons and I want to switch between two different modes or something like that, and I want to kind of build up some logic. Well, Siemens has you covered because they want you to be able to do any system that's possible to do. So what they have is this little thing called free blocks, And man, I'm gonna tell you, people don't know these are here. Yes, because free blocks are logic function that is built into the drive, and you have to understand how to use BICO in order to use them. So that's why we're talking about them now. So, I mean, there's some pretty simple things like ands or ors, things like that. So like an and, you have a couple of just Boolean and blocks. You have four input and blocks that are available to you. You have four input or blocks. You have four input exclusive ors. And then you have a couple of inverters. So, and I'm not going to go into too much on this because it's kind of a totally different topic. But if you have some digital logic operations that you're wanting to kind of handle based on switches and inputs and feedbacks, and say, for example, you could write up a fairly simple digital logic program that controls a conveyor belt based on some proximity sensors. Bring those all back into the G120 inputs, and then use these free function blocks, use the controller, the technology objects, and then you just control them all, and you don't need a PLC. You just need the drive. You just need the controller that you've already bought. And so, yeah, that's what you have here. And here's the crazy thing. That's just the digital logic stuff. Click through here. We have arithmetic functions. You have adders where you can add percentages. So if you have like analog inputs, or you're bringing in some sort of value somewhere else and you want to take the actual speed and then scale it somehow and blah, 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 all this different stuff, you can do that. You want to take the absolute value of something. There's the absolute value blocks in here. There's all sorts of stuff, multipliers, divide, all of this. We even get into, excuse me. That was one thing I was talking earlier about. Hans' wonderful live stream from PLC Skill Tree this last weekend, and he experienced the streamer tickle. It's bad. After you've been talking for about an hour nonstop, it starts to get worse. Sorry, excuse me. So you have all of these different functions that are just available to you as long as you know how to use BICO. There's even some like really, really crazy stuff. And this can, for simple applications, replace the need for a PLC. Because you also have to remember your HMI. If you're using a Siemens HMI, you have what is called direct parameter access. And so, don't tell anybody this, but you don't need a PLC to pull data onto an HMI. So you can actually pull values straight onto an HMI from a Siemens PLC. It's just a little trick of naming your data blocks or naming your tags a certain way in the tag list of your HMI. So even if you want an HMI, you still don't need a PLC for very simple applications. But don't tell anybody. But we also have complex functions. What is a complex function? Oh my goodness, we have a limit monitor. Oh, so you can actually have logic that's saying, hey, if my speed, give me an output. So this is kind of like a, I guess a CAM function built into the standard performance off the shelf. You get it for free when you buy the G120 CU. There's also some like stuff in here that I saw in the function plans. Numerical switch, binary switch. So here's a cool little thing. a binary switch. I'll show you how to use this. because you're taking and maybe it's a numerical switch that I'm wanting. Yeah, this is what I'm wanting. So the numerical switch. So here's the way that I've used this. On a couple of other streams, I have talked about load sharing applications. So if you wanted to set up a load sharing application with, say, you could do it up to, I mean, I guess you could do 3 or 4. I guess you could do 3 or 4 applications, but say you wanted to do like a 2-axis load share, you would not, and you put 2 G120s on, you wouldn't even need a PLC for it, because you could take and pass the output, because guess what, you have an analog output on these things. Input outputs, analog outputs. Oh, look at that, you have 2 of them even. So you could take that analog output, and remember, you would take the you have to have a set point from somewhere, but you need to have the torque limit. If you are the master, then you get 100% torque limit, right? Well, if you are the follower, if you were trying to load share with the master, you need to take that other value in. Well, what you could do here is you could say by default 0 is 100%. Okay. I'm going to take in an input, and this is where 722 comes in, because that's going to be our input. We're going to bring in an input. Input status 0 is whether or not it's the master, or which one's the master. So when the input's low, this one is the master. That's what this is saying. And then from this one, we're going to take BICO in, and we're going to go to 755, and we're going to bring in our analog input 0, except this time, our analog input 0 is actually the output from the other drive. So if you swap this over to 1, then it's going to take whatever this analog input is, and now we can go here, click here, go to BICO, and connect it to, oh, look at that, current limit variable. Would you look at that? It's almost like this was an intended way of using it. And it says, all right, look, current limit variable is set to 100%. Do you want to change it? And I'm like, and we'll cancel this. But that's how you do that. And so you could literally do a load sharing application with an analog pot, a switch, and some wiring, and 2 G120 drives. Well, I mean, I guess you'd need like start and stop and all that stuff too, but you wouldn't need a PLC. We've done that sort of application on the S120 using BICO to swap in between, because in S120, all of the parameters are on one control unit. So the drive object, like the different drives, are just kind of different areas of memory. And so you just point it to drive object 1, drive object 2, drive object 3, parameter 4, 5, 6, whatever. But here, that's a load sharing application using BICO, the free function blocks, and not even having a PLC on 2 G120s. How about let's just go ahead and do that? I mean, we probably got at least 30 minutes that we could do this, and I don't even know how many people are on. Oh, we've got our regular. I feel like we've got a regular crowd. I love it. I love it, crowd. So let's go through, and because the members do get this archive, I'm gonna go through and actually just set it up. Let's just take another one of these, and let's go. Drive 1, and then we're going to take, and we're just going to take this whole thing, Control C, Control V, drive 1, drive 2. Okay, and probably didn't want to do that. Hold on, let's do this. Because I want to go back and reset something real quick. Oh man, we're out of music. Dun, 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 dun. And let's go back and change this because I kind of jacked this up earlier. Go back and set all this to 0. Because I don't want you to actually go through and try this out and it be wrong. All right, I'm gonna move my head. All right, so let's go through and set this up because here's how you would do it when we kind of already did it. So we've got this numerical block. Let's set this up first for drive control, digital input, jog. So, in which, let's show you this whole kind of setup. Why did that not save? Hold on. Hold up. Make sure we're doing the right things because I'm going to go, and there's a couple of different ways of going at it. I'm going to go at it from this way because I want this connected only to, I think it's, what is it? 8 on, off 1, this one. Okay. And I don't want it connected to this other one. And so that's going to be like on off, so that'll be like a selector switch. Turn the system on. Then we're gonna bring in, we need a speed set point, right? Let's be a good workers here. And you know, I'm sitting here thinking, one thing we are gonna run into, we don't need Profibus or Profinet, and that's going to give us a little bit of trouble. So let's do something real quick and go into the commissioning wizard. And I want to go, we're just going to click all the way through to the very end where it says, not here. I skipped it. I clicked too fast. Here. I don't want field bus. I guess. All right, whatever. We'll just do it this way. Okay, cancel. That's fine. I thought there was a way that you could set to where it's not using the field bus, but it's apparently not needed. Sometimes the start drive stuff, like I mentioned before, I haven't been using start drive nearly as much as I have starter. So let's call this digital input. I want it to be our off 2, just as like a safety thing, you know, that stuff. So coast, we're going to do that. Source 1. So that's going to be our physical e-stop, and it's saying, hey, you're replacing this with this here. And you know, I remember what I need to do. We're going to go to, and sneeze. Somebody's freaking smoking weed in here. Idiots. Do what you want, but in a public space like this, it's kind of obnoxious. Which in Georgia, it's illegal anyway. But the we're gonna do, I'm trying to find the communication is way down at the bottom. So what I'm wanting to do is set our our Telegram to a 999 because I want to be able to change everything. Because I'm going to show you what happens, because these are already like tied into a lot of different places. Like this off one, or sorry, this no coast down, no quick stop. Like all of this stuff has to be reset. And so that I'll show you here in a second on this interconnections. We're gonna look at the inputs, and again, this is BICO, your interconnectors binectors connectors, and so these are your bits coming in. And right now we are set. So this one I want to set it to 1 because I'm not going to be using my field bus. So I need to set this one to 1. I need to set this one to 1. This is the off 3 quick stop. Enable operation. Yeah, we'll set this to yeah, we'll just set it to 1. When it powers up, it gives it the ability to it's not going to be controlled by PLC, and I think that's it. There might be cancel. Here it is. Enable ramp function generator. Because if you're not using the field bus, all of these will be set to 0 when the field bus is set. And I said the wrong thing at the wrong time. Continue ramp function. And if you're using the analog input like we're going to set up here in a second, these won't work. Like this will cause you to keep you from running. And I might miss something. So definitely if you are needing to actually run, or you're wanting to test this and run it, you may run into some stuff because I'm not being thorough and I'm doing this off the cuff. So I'm trying to be as thorough as possible, but I'm probably gonna miss something. So let's go back up to the inputs now, and because I want no coast down, so that one I definitely want it being controlled. That's just kind of our e-stop. Everything else that was that way. We need a reset. Okay, so we could also do this right here. I'll show you something on that interconnector or the interconnections. Go back to the binector, and then let's go to acknowledge faults, which we could have just looked at over there, but our acknowledge fault. All right, I'm annoyed. Here's why I said I could have just looked at it over here, because by default it's set to this input 2, so it's parameter 2103. Yeah, so 2103.1. And what I want to do is I want to put it to our 723.0, because when you turn the thing off, that input will go high, and so that'll be, you turn it off, it resets, auto reset. You don't need an extra button. So 2103, or we can just click over here. Sorry, 2103. This is another way of doing this. You can pull this down. Click here. So this, we don't want to be a 0, but it's gonna be as well. I guess it doesn't matter for this one. And then this one, we actually want to change this to be R723.0. So that's the inverted status. So anytime that you stop this thing, it's going to perform a reset. So you don't need an extra value there. And then let's go back to our functional view. I was like, why is this not there? And so now we can use this for whatever we want. And let's use this digital input 2. We're going to use this later. Let's just disconnect it right now. 2104. Where's why can I not read numbers? 2104 right there. Disconnect that. And so, all right, so because we're going to want to use that for this the changeover. So let's go back to our drive functions, not drive functions, application functions, 3 blocks. And then let's click on this numerical here, and let's do this little swap and go to BICO 722.012. 722.012. So 0, 1, 2. in my mind, see, I've been working with Siemens drives for 24 years, and I still have to think about 0, 1, all of this different stuff. Anyway, so that's that switch. So now we have where our torque limit will come from. So let's look at this. 20,220, and we're wanting to put this in our torque limit. Oh, I guess it's current limit. Oh, I mean, I guess we could just put that current limit variable, or I guess, where is that current limit variable? Interesting. It's because we're in volts per hertz. So let's go to speed control encoderless, and then that gives us this torque limitation right here, because that's really what we want. We don't want this, and so we're gonna go through and say, all right, our upper torque limit right here is gonna be that 20,220 right there, right? Well, if you've looked at my my live stream of how to actually set this up, or how to set these things up, you know that what happens if you put a negative torque limit in as your upper torque limit? Bad happens, and bad happens pretty quickly, and bad is not something you want. Bad is bad. So what we have to do is actually do an absolute value of this thing, and then put that value in here. So let's go ahead, and since we're already here and I know where this is going to be AVA output 0. We're going to do that, and then now we're going to go back and take this and tie it into our numerical switch. We're going to tie that into AVA input, AVA 0 input, blah 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 blah. Where is it? AVA input, blah. There we go. And then now that's set. Woohoo! But we got a couple of little things that we got to do. First of all, is that set right? Blah blah blah. Okay. We need to saturate our speed controller. Okay. So we need to saturate our speed controller, which means, let's see, what's the best way to do this? We're gonna want to use this other switch. When we're the master, we run the actual value, our speed set point. Right? So in this case, when we're the master, that is when BICO 722.2 is good. We're going back through. So that 722, that's when we're the master, or I guess, yeah, when it's 0. And so that is going to be our speed set point is coming directly from our 722, sorry, analog input. I'm going to change this value here. So it's 755 as a percent. I'm going to put this here and then come up here, because what we're going to do is we're going to change analog that one. So all right, let's see. So that's when it's the master. This one, we need to do a multiplication, right? Because we want to multiply by like 3%, right? So let's do that here. Let's go to a multiplication, and let's do like there's like a fixed percent. Where's fixed percent? Fixed value. There we go. We'll just do 5. And then we're gonna take and do our blah 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 722 1. And remember, if you're unfamiliar with what I'm doing, look at the load sharing live stream, because that's very much, we're just kind of manually doing this. We're taking and saturating our speed controller in order for the torque limit to always go in if we're a follower. But yeah, so we kind of know all this from that. If you're unfamiliar with what it is, you can continue to watch on and then flip over and watch that live stream on load sharing. It's actually one of my more earlier applications that we went to. Look at load sharing and the winder live stream are both have to do with this. So got that. That gives us a 5% saturation. Now we need to reconnect that here. So let's go connect this into the input of our numerical switch. Numerical switch 1 input. That's NSW input 1 right there. So there you go. So now when we come over here, and if you notice, I'm trying to show you both sides of the binector. There's here, I can take, this is kind of like thinking of it like with the little connector this way. And then I'm saying, hey, what do I want plugged here? And then I'm plugging something in here. And if you notice, when I'm doing it from this side, I only get one option, right? So it's one plug. You can plug it in to one thing. If I'm doing it from the other side, which I'm about to do here, when I select my main set point, I can actually select like multiple places where this goes out and connects out to. And you can kind of think about it one way of like an input can only have one input, but an output can be looked at by many different things. And so that's what's going on here. Definitely don't want those. So let's see what main set point. Bam, right here. There we go. Look at that. Yeah, of course I want to replace that Profi drive crap. So the way we have this set up right now is with these switches, our main set point is going to be coming in here to our analog input. And if this is the master, this will be 0. Okay. And so that'll get passed into the main set point. Well, if we are not the master, we need to take whatever the set point is and try to run faster. That's in the load sharing. And that's why we did this little multiplication. All right. So before we get too far along into this, because we're about to kind of skip away from the free function blocks, we need to make sure that we're doing some runtime groups. for these, all what runtime groups is how fast it gets calculated. And so these blocks will get calculated in runtime group 5, and I'll show you. I don't think they're adjustable in here, but in the S120 you can adjust those runtime groups. But yeah, so this just means that these will actually get executed. The logic will get executed, and then we did a multiplier. We need to set that to something. And then we also did an absolute value function, didn't we? So we need to, where's that function? There it is. So we need to do that. So that is the basics. So we've got our switches. So we've got our main set point set. So it's going to run faster. It's going to try to run faster, but it's going to be torque limited if it's the follower. Okay. And then, and then otherwise it's going to try to run 100% torque, or not try to run 100%. The torque limit is going to be 100%. So I think that's it, right? I believe it is. Force cell at the middle that detects how tensional my wire. Is that a cable winder? So we got a question while I'm finishing up this winder portion. That's similar to the dancer question that I had before. I'm not sure in the LCON block. The question is what LCON function to use for a winder with a force cell at the middle that detects how tensioned my wire is. And that's the exact same concept that we were talking about before with the dancer. You're going to need to use a PID function for the speed of one of those winders. So you can either do a trailing tension to where the downstream process controls the tension, which means if there is less tension than you need, you would need to speed up. Or you can do an upstream, like my application or my example a minute ago, and you would want to trim. So you would set up the PID, take the force sensor, and that would be your feedback. And your output variable would be the speeds, the speed set points. And then you would have your line speed set point would be the feed forward thing that I talked about. If you weren't able to catch up, like I talked about this a little while ago, look for me waving my hands around like that. And it's the same concept, and it uses a PID block. And so I'm not sure the LCON function, that library block, I'm not sure exactly what it would be, but you could do that with the block like the LCont C, the continuous C function, and yeah, that's just a regular PID block for that. Or if you really wanted high speed, like closed loop control, this is how you would do it. You would be using this technology, the technology function that we did before, which brings up, there's actually an application that is interesting, because on an S120 you can do all this stuff, and you can bring in the PIDs and do all of that. Cool. There was an application, it was very small wire, and I didn't do this application, but this is one of the legends of Siemens in the U.S. His name is Carl Owens, and he has since retired, but he was one of the best that I've ever met. And he had an application that had like this really small, almost like guitar wire, and it was like so tight, and it was stretched out over the course of, like, I think it was like maybe like 10, 15 meters like across, and in the middle of it there was this sensor, and so you would know that wire would just like bounce all over the place, and it was a tension control application, and he was able to do it. So another drive manufacturer that shall not be named literally could not accomplish this to get the tolerance on the tension control. Carl went in there with Siemens, put a Siemens drive on it, and went in, and before lunch had it within tolerance by using the built-in PID functions and the analog capabilities of that. And so he brought in the force sensor into the analog input like we did earlier for the PID controller, tuned it out, and then it still wasn't quite there, and so he put a resonant frequency bandstop filter for the length of the wire based on the tension that it was supposed to be at. Oh, beautiful. I love it. I love telling, like, and the crazy thing about it is he did it, he tuned it kind of manually, but there is a function built into the S120 drive that will actually detect those resonant frequencies, and so you can actually put in those bandstop filters. But anyway, you may have to do that depending on how tight your wire is, because if you have a long distance between the two, you can start to get that like guitar effect to where your sensor is actually actuating that guitar or that wire. So let me get back on task figuring out what this is. Great question though, because that does go along with this topic of using high performance stuff. My goodness, it is almost 4 o'clock. I went from, all right, I'll take another 30 minutes to, oh no, never mind. It's about 30 minutes. Let me do the last thing because I feel like I'm missing something on this. What am I missing, chat? What am I missing? I've got my torque limit, my speed limit. I think this is it. Let me look at my set point path because I'm pretty sure this is it. Let's go up to operating mode, control mode. Let's just go through this path. So we've got our output from our switch will come in, and then that comes here, goes through ramp, all of that garbage, normal stuff. We tune all of this like normal, comes in, our path, our upper torque limit should be that absolute value. All right, that looks like it, chat. So now what we need to do is we need to go back into our device networks. We do Control C, Control V now so that we don't have to do all that crap twice. And then we go and change one place on this guy. Oh, I remember what we got to do. Whatever. It's not that big of a deal. We got to change our analog outputs because these have to know. We have to know which one's which. So we're gonna go in. Let me do this again. Yeah, delete it. So our analog outputs, we want to put out from one drive. Actual speed? No one cares about your actual speed. We want our actual torque, which is like 72. Current 79. Nope. There. 81. I think that's it. Because yeah, we need our actual torque coming back. So like that's torque utilization. No, torque actual value. That's what we need right there. So we're spitting that out. We're spitting that out, our analog output, and then that is, we will tie 0 to 0, and then that will give us our analog input is coming in, and it's tied into our first switch, which is our torque switch. Nope. It's not. That's our speed set point. Lies! Okay. So 0 will go to 1. That's how we'll do this. 0 will go to 1. So when we wire this up, our analog pot will go to both analog inputs. That voltage will be the same. Analog input 0 for both of them will come from the pot. 0 to 10 volts. Actually, negative 10 to 10. So we'd have a bipolar voltage there. So we have our pot there because we want to be able to run backwards, reverse, forward, backwards, all of that. So analog input 1 will come in. We will tie that into analog output 0 from the other drive. And we'll do that on both of them. And then our start and stop will be the same. Our reset scheme is the same. So now we are ready to do this for the 5th time. And go in here, save that. We do need to change one thing because our inputs and outputs, we need to swap the logic for this whatchamacallit, the master control. So we're gonna go to application functions, free blocks, our, what was that under? Switch functions, numerical switch. And this right here, we need to change both of these to the inverted version. And then everything else stays the same. So this is going to be 722.2, so it's 723.2. So we just invert that. We take the inverted version, 723.2. And there we go. Now if we wired this up, if we went through and wired this up, again, we would have our start stop would be on input 0, our e-stop would be on input 1, and our master, call it a who's our master? Side left, right, and then that would set things up that way. So, and that's it. So, like, that is a lot of information, I know, and yeah, I feel like that's overkill for a conversation about BICO. BICO is the way that you can reconfigure and program Siemens drives, and it is simply connecting inputs and outputs inside the drives, just like you would a PLC. And I totally did not even like think that or plan on going through and doing that load sharing application, but when it comes down to it, that's kind of the easiest way to kind of show all of the different features. We've gone through and looked at the free telegram. If you haven't seen that video and you want to know more a little bit about the power of it, setting up free telegrams is one of the coolest things that you can do using BICO as well. And you don't have to have like some crazy function, because a free telegram, you can send over all sorts of crazy information to your PLC that is not normally available. And if you're using an S120, I think in my free telegram live stream, there was a, I was setting up a control telegram using a custom UDT that was in the project. What's up, LFC? How's it going? It is good to see everybody in. I don't know if you're live. If you're not live, then hey, from 2 hours ago, because you realize that, like, if you start a live stream, your chat, and when you chat, it comes in live. It comes to the future. So anyway, I appreciate everybody this conversation. It's been fun. BICO, simple but powerful, and like, I'm sure that there's an analog to it in other drives and other manufacturers, but I just always took it for granted, but that was available and you could configure however you wanted to. And I will say, kind of to kind of the chatters about that force cell on a wire. In general, your like on an S120, your control loop is on the microsecond range, and your PLC is going to be on a millisecond range. So you're kind of like a couple of orders of magnitude difference between the speed of doing something in a drive versus doing something in a PLC. Now, 20 years ago when I started doing this stuff, it was extra orders of magnitude, and it's always order of magnitudes because you're dealing with communication otherwise, or you're dealing with some other analog conversions. You're adding in steps. With a drive, you have one analog conversion in between it, and that analog conversion is down on like the nanosecond range or microsecond range, whereas on a PLC you may be looking at millisecond ranges on that conversion, and then you have to encumber a cycle of your PLC, then you have to encumber a transmission cycle, and then you have to encumber another servo cycle or whatever on the actual drive itself. So you just kind of stack up all of these delays, where it used to be the only way that you could do dancer control was this way. And what's crazy is one of the first projects that I ever worked on did a dancer control, and I didn't know any better. I was 22, something like that, and I didn't know any better that you couldn't do dancer control on a PLC and pass it down to a drive. I just didn't know. So I set up all of these functions, and it just worked. It worked really well. and the reason I say it that way is because my dad, I talk about him on the stream all the time. But he told me, he was like, I told him about how I set it up, and he was like, oh, well, that's probably not going to work. Like, you gotta run it in the drive. The PLC is not going to be fast enough for that. And I was a little confused because I was like, no, it's running. Like, it's working. And so I was like, is it not supposed to work? And he was like, no, I've never been able to do that. But it was one of those things to where he had worked on the previous generation processor, and it absolutely would not work. Dancer control could not work on that. Which, Lucid, if you're still on here, you need to replace your 505. Yeah, get rid of your 505 in your plant because it's slow. But the project that I did was using a newer generation PLC, and the communication was faster. So the Profibus communication I was using, because again, I didn't know you couldn't use the high-speed communication. I was using the 1.5 megabaud, where he was always using the 115K. So it was a 1,000 times faster, or whatever it is, or 10 times faster, and it just worked. So you may be able to get your PLC working without these sorts of functions, but especially with like the 1500s now, like they just upgraded even the lower performance processors in the 1500, they kind of like did a ninja edit on their firmware and unlocked the dual core capability, and now basically just doubled the performance just with a hardware download, or a firmware download. And so so you may be able to do that tension control, bringing analog inputs into the PLC and passing it down, especially if you're using isochronous Profinet. Like, there's a lot of things that you could do to kind of speed that up. Also remember that your fastest connection to the process is at your drive. And with an S120, you have those tools like the current, which is the lowest control loop. So it's the fastest control loop. You have a current set point band stop filter. So you can do frequency domain harmonic elimination at the current controller built into the S120. So kind of crazy, kind of cool. And that's what Carl was able to do with his little banjo wire. So anyway, I really appreciate everyone that's been on. It's been a good stream, a good bit of chatting in here. I do want to give a shout out again to all the members. I do thank y'all for what you have committed to, and you see the gold stars. You have the gold stars. Well, I guess technically they're black stars with gold outlines, but yeah, you're good job. Like, I appreciate it, and I'll be real. The money is great, like, that you bring to it, but that really, being a member, makes YouTube put this content out there more, and that's the greatest benefit I have. So I always want to give you the ability to get something out of it. And members, I will be archiving this and getting it up into the member directory just as soon as I can. And you've got a couple more videos, and I'll probably won't record it tonight. I'll probably record it tomorrow. But the first video in the series on kind of business development and everything, and that'll be available to all the members at all the different levels. And so if you made it this far, thank you. And if you made it this far and you're not subscribed, I mean, just check, because, like, for real, like, you would watch this guy for that long and not subscribe? Really? Yeah, well, anyway, I appreciate your time, and I appreciate just the support for the channel. We're growing, and I didn't mention it before, but the Discord is also growing. Like, it's growing daily. I've got the little hidden channel where it tells when people are joining in, and it's always, like, lit up. And so it's good to see the growth, trying to help people out in this international community. And yeah, I appreciate it. Y'all have a great weekend. Y'all be safe, whatever you're doing. Here in the US, stay warm, or I guess anywhere in the northern hemisphere. If you're in the southern hemisphere, if you're in Brazil, like my buddy was, like, texting me on WhatsApp, and he was like, oh yeah, I went back down to Brazil. And I'm like, why? He was like, because I wanted to surf. And I'm like, oh yeah, that southern hemisphere thing. So if you're in the southern hemisphere, stay cool. Go drink some water or something, because it's probably getting hot. But anyway, until next time, y'all take it easy. Have a great weekend. And if I don't see y'all another stream before the Christmas holidays, Merry Christmas, Happy Holidays, and y'all take it easy.